So let's get started and let's see. So the missing data can be replaced by using the fill NA method. So you can see here that there might be a case where some of the data is missing, right? So if you see in the thing below above, there was a column which didn't have any data. It had not applicable or none. So missing data is one of the most key feature which you will see in the real world. In fact, missing data is one of the most critical component which exists, right? So here in this particular case, you would see that there was a missing data here which was shown as none previously. And let me just show you before. You can see here. So you can see here it was not applicable because we have put it as none. And you can fill in those pieces by using the feature which is fill, which we just showed it to you, fill NA. So wherever there is not applicable, you can fill those values with certain. You can in fact fill those values with say average of that particular column or average of that particular row or median, right? These kinds of techniques are very heavily used by the data scientist. Or you can drop that column altogether. So if you find that that particular column you don't need to use because it will add some bias to your overall training, then you can drop all of the not applicable columns. So from a stats perspective, again, you can calculate different kinds of statistics for a series. Like you can see here, I have an NP range and it from up to 10 and it's of type float. And I'm creating a new columnar set by calculating the mean, variation, standard deviation, and you can add many more functionalities like that. So you can see here that if I had a series of data, and so I can create the mean of it, the variation, standard deviation and all. And in fact, if you have a particular column like this, you can basically just say describe, and that describe basically gives you all the characteristics about your columnar data, like how many values are there, right? For A, B and C, what is the mean, what is the standard deviation, what is the minimum value, right? And where's 25% of the data, 50%, 75%, what is the maximum value as well. So you can use the describe feature where it will give you a lot of statistics about the overall table that you have. In fact, to all of them, you can use a particular feature which is s.apply map. This apply map will basically apply this particular formula, which is if you are a programmer in Python, you would know how to write lambda functions. So what it is doing is that it is basically doing this operation where I'm applying to each and every row this particular calculation. So if I just apply the map, so you will see that it has taken and it has basically applied this, which is x power of 2 plus x divided by 2. So it takes that value and apply those element to them, and then you can see here, in fact, rather than writing a lambda function, you can define your own function, like here saying that I want to add 10 to all of the numbers, and I can say s.apply map, which means I'm going to apply this to every row, a particular function which is add 10, and then it will apply those, and you can see here that for every element it has basically added 10 to the original data frame. So like pandas, cuDF provides string processing methods also, and we are going to look to certain extent the string part. You can see here cuDF series ABC, certain elements. Again, there is a none here, and if I just run this, you can see here you have print s.str lower. So what it does is kind of already known that we are taking the values and we are converting them into lower strings, right? Or if you want to count the bytes of each and every string, sometimes you may go out of bound in terms of the memory, so you can in fact count the number of bytes which were used for storing that particular string if required. You can write different kinds of regular expressions, like you can say, see if my string contains this particular regex or not. So it should either contain this or that, and it will only print the values where that particular thing is set. So you can see here in the first go it is saying false because there is neither C nor dog, and you will see that for the third one it is basically true because there is a C there, right? So it consists of C, and then there is a dog at the 7th location which is also been set to true. So if the dog value is also set to 2, which is the 7th row, while there is a C as well in the 6th column, and that's why even 6 has been marked as true. So you can do different kinds of regular expressions using the data frame there. Okay, so this is kind of an easy one, so I'm going to skip that part. And obviously you can do things like concatenation. You can concatenate. So here you can see here, I have a cuDF series 1, 2, 3, and then a not applicable N5, and then I'm just concatenating it again with itself. So you can see here 1, 2, 3, 4, 5, and again 1, 2, 3, 4, 5. So you can concatenate to itself, or you can append in the end if you would like to, which is almost the same that we did later on as well. So this is another example where we are trying to do a join operation. So it is more of like a SQL syntax. So if you are a database person, you would understand the SQL like queries. But the main thing is because everything runs in parallel, the order is not maintained. So you don't get guarantee, like if you do anything in the SQL database, your columns, the rows are kind of, the order is maintained. But here, whenever you fire a SQL like query, the orders are not maintained because they are basically, how should I say, they are basically happening in parallel on the GPU. But if you want, you can restore them post also. So here you can see here, we have created a data frame. You have a key and value pair. And then similarly, you have another data frame B. We have again a key and value pair. And then we are trying to tell to merge them. So we are saying df a dot merge. So merge is one of the most common operation that you find in your database. And we are saying it how to merge. So we are defining the strategy, how to merge it. Whenever there is a necessity of merging, should I add it to left, or should I do a left merge, or should I do a right merge? So if you are familiar to SQL database, you would understand some of the points which I am trying to mention here. You can see here, you have A here and you have A here as well. So you have the value 10 and you have the value 100 here. So we have done a left merge based on the key value, and that's how it will work. And you can see here, if there is no value of certain components here, like there was no value for B here common, and you will see that B have been populated with not applicable. So only at the places where you got the values is kind of in the beginning, and you can see here that the order was not maintained. In the beginning the order was A B C D E, but now you see A C E B D, which is slightly a different order, but it is done something called as a left merge for you. So moving to the next one, maybe, so like pandas, cuDF supports split. So this is another example of grouping. You can see here you have two columns here, aggregate column 1, aggregate column 2, and we are saying set it to 1 if x mod 2 is 0, which means if it is divisible by 2, then set it to 1, else set it to 0, right? So that's what this particular logic actually means. If it is divisible by 2, set it to 1, else set it to 0. And if you want, you can do a summation of it. So ideally, yes, for all of them, you will get a summation of how many values are aggregated column, how many values are 1, and how many values are 0 here, right? So there are different kinds of exercises that you can do. This is another example of time series data. So here you can see a data frame supports date time. So date time is another very common component used in the data sets. And you can see here we are using pt.data range. So this is the data range I'm setting starting from this particular date. The period is kind of fine, the frequency is defined, and if I print the value, you will see it. So this is the date, And you can see here we define the range with a period of 72, and it keeps on moving forward here. So you can define different kinds of dates as well. Okay, so I think I kind of covered a large portion of what all functionalities are provided here. As I told you, there are other kinds of features also which exist, like you can, if we had covered to certain extent prior something called as cuPy. So in case you're writing your own GPU code using a package called as cuPy, you can basically convert your frames between cuPy to a data frame so cuPy has this concept of ND array, n-dimensional array. So you can do those kinds of conversions if it is required. Or from pandas, we have already told you about it. So you can convert from pandas to cuDF, or from cuDF we can convert it back to pandas so that you can utilize it on the CPU, say for different purpose like writing it to a file or something. Same thing exists for NumPy. In case you want to convert a CUDA data frame to a NumPy arrays, you can say here, you can say df.as matrix, and it will basically do the same thing. So there might be certain deprecated warning, but it is fine. But you can convert them as an array. So you can see here, you can convert them as an array from the data frame as well. So that kind of a functionality is also provided. We also talked about reading or writing from a file. You can see here that we are reading from a CSV file here. So it's quite easy if it exists. So we are saying data frame dot to CSV. So here we are actually writing to a file. So we are converting it and writing it to a file. Or if you want, again, whatever we have written in form of a file, the data frame, we can read it back and it should ideally print the values that we had on our data frame of A, B, and C. So you can see here it is just printing the top values, and then you see dot dot dot, because there are so many values, it will not print all the values. So the print will not print all the values. It will only print certain head values, and in the end, whatever values are there, but it will print the overall thing. So it says you have 10,000 rows inside it, out of which I am kind of presenting you only a few of them. But one of the critical reasons why I told, so far I've been telling you about how to use cuDF, but what is missing so far is the part of performance. I just told you that it's used for performance. So far we were reading 1,000 rows, 10,000 rows and all. But cuDF is all about performance. And if only if you're doing certain complicated operations on it, or if you have a large data, that's where it will make sense. And here, as you can see here, first we are going to run a NumPy based thing, a pandas based thing. So we have created so many 10 million values, and those 10 million values we are populating in the pandas data frame as well as in the CUDA data frame, and we are going to do a sum operation on pandas as well as on cuDF, and we are printing the time for it. So let's see how much time it takes. So you can see here it has taken 790 microseconds on the GPU, and on the CPU, let's see how much time it takes for calculating a sum of 10 million elements. So 790 microseconds on the GPU, and it has taken 15 milliseconds on the CPU. So you can already see the amount of timing difference when I try to add only just one column. It is really good, right? But it is still a simple example. So let me now show you a more realistic example of sensor data analytics. So what we are trying to do here is that we are trying to mimic as if you are getting data from various sensors, and it is getting from a series of sensors at every milliseconds, and these sensors are measuring, say, temperature, pressure, or something, right? So what we are doing is we have a pandas data frame. We are creating a date range. It starts at this particular date, it ends at this date, and the frequency is in milliseconds, right? So this is going to create a date range, and the same we are creating the date, the values, it's kind of sample values, and then we are going to populate in hours and minutes also. So let us create them in the pandas side of it, And then what we are saying is that we are going to just do certain analysis on it. Like here in this case, we are just saying I want to group by based on hours and minutes. I want to do an aggregation, and the aggregation type is of max. So I want to find the max, right? So I want to do aggregation and I want to do a max value of it. So you can see here creation took around 19 seconds, and then I'm going to do a perform an operation on it. So I'm going to do a group by on hours and minutes and do aggregation based on the max value here, and it's going to take some time to finish it, right? So at the wall clock time, it took around 4 seconds to do that aggregation that we just talked about, right? So let's do the same thing on the GPU and see. So you can see here on the GPU, it has already finished, and it is not even in seconds. It is actually 23 milliseconds versus 4 seconds. So the group by of this particular case took around 4 seconds, and on the GPU it took around 34 milliseconds, right? And this is one of the part which I wanted to show, was that even though there are so many functionalities, but one of the most critical thing also to understand is the part that the primary reason where you will use it is when you want to do certain complicated operations, or you have large data set which may take a few hours to few days also to do these kinds of operation, and that's where cuDF makes its impact. Now what if this particular functionality which I just talked to you about is not present? Like I showed you so many functions here, string functions, this function, that function. What if you had a custom operation that you wanted to do on the data which exists? In that case, you can also define something called as user defined functions, and you can define your own complicated functions, and you can use one of the features which is either apply rows or apply chunks. So either we'll use apply row or apply chunks, and I'm going to show you very quickly on what that means. So apply row basically processes each of the row independently in parallel. So if you remember, GPU computing is all about being in parallel, running things in parallel, right? So if I call apply row to a particular data frame, and if I define what is going to happen inside that apply row, that method, that row calculation will be independently happening in parallel on the GPU, right? And it will optimally divide the columns into chunks and assign those chunks to different GPU blocks. And what are these blocks and all? I will talk about that in a bit. But one of the most critical thing that I have to say, and again repeat that I told in the last thing also, is that the execution order of row is arbitrary. So each execution of the function must be independent of each other, which means that you cannot be saying that I am dependent on a value on row 1, and only once I have that value, then I can change the row 5 or so. So if you have a dependency among the rows, you cannot use that. So cuDF under the hood, as I said, would depend on CUDA behind the scene, and it's going to run it on the CUDA architecture. And what happens behind the scene, it is run across multiple blocks and threads. I will quickly say what a block and thread concept is in a bit. For now, you can assume that something runs in parallel in terms of blocks and threads, and then it makes use of a package called a Numba. So Numba is the one which what it will do is it will actually do a JIT compilation, just-in-time compilation of your function which is supposed to run on GPU, which you have defined to be used in the apply rows, and it compiles it to lower level CUDA code, which finally is given to the GPU. And how does the function look like? It will basically look like this. Whenever you're defining a function that needs to run on GPU in parallel, you will have certain input columns like this. You will have certain output columns, and then you will have certain additional arguments that you want to pass to your function that needs to run in parallel. And then you will have for I, and then you will do the operation that you want to do in parallel across all the rows. So And how do you call it? So you will call it in this fashion. You will say apply rows. You will define the name of the function, which in this case is kernel. And then you will say what are the input columns. So you will create an array of it. So you will say in columns, in 1, in 2, in 3, the number of columns that you want. Then you will define your out columns. And you can see here for the out columns, you are also defining the data type. Like you are saying that the output 1 is of type float 64 and the output 2 is of type integer 8 bit. And you will also define the input additional argument that you would like it to have, right? So the outputs are not returned back. Outputs are also passed as an argument in case of CUDA world, and that's why even to apply rows, you pass it as an as a argument here, right? So this is an example of, in case you, for a data frame, if you wanted to represent the pairs of longitude, latitude and longitude here, and you wanted to calculate the Haversine distance, so you can, if you click on this, it will take you to the Wikipedia definition of it. But you can see here basically what we are trying to do for the latitude and longitude. So we are trying to do here certain sine and cosine functionality here, where we have these variables as latitudes and we have the gamma variables as the longitudes here. So you can see here from math, we're importing cos, sine and different functionalities here, and then we are creating those latitudes and longitudes, and then we are defining our function which I just told you about. So we are doing the, we want to do Haversine distance function, and you can see here we have a couple of inputs: latitude 1, longitude 1, latitude 2, longitude 2, and we are trying to find the Haversine distance between them. And this is where the output or the Haversine distance is actually put and given as an return back as a output. And you can see here we are saying for the x1, y1, x2, y2, which is latitude 1, longitude 1, latitude 2, longitude 2, and I'm doing certain additional calculation here. I will go through certain details of CUDA tomorrow so that you get an idea of what I'm trying to say here. What is this thread ID and block ID? Maybe I will show it to you tomorrow. In the tomorrow, not in the tomorrow session, but the next session, which is happening on Wednesday. And what I'm doing is I'm getting this value x1, y1, x2, y2, calculating those distance, the sine and the cosine transforms, and by finally storing the value here, right? So what I'm saying is that I want to take this function and I want to calculate this Haversine distance in parallel, for which I am doing something called as apply rows. When I do the apply row, I am giving it the input columns, which I just had. I am telling it for all the columns in parallel, I am going to calculate this Haversine distance. The output is of type dictionary, and it is having a data type float 64. And this is the part which I am just passing to it, and I just need to run this. And I'm going to again run this, and it's going to do it in parallel. You can see here that it is calculated in 798 milliseconds, and in fact the second time it becomes much faster, 14 milliseconds, and it is basically going to print out. So if this is your latitude 1, longitude 1, latitude 2, longitude 2, this is the Haversine distance which is calculated as the output here. So we have done certain printf statements also, and I'm not putting those printf statements here at this point of time. There are certain outputs. It won't display them in the Jupyter notebook because the printf statement will only appear in the terminal output. So only if you run it on the terminal, these values are going to be outputted. It doesn't get output on the Jupyter notebook. But I'm going to talk about it later on. But once you run this, you would understand that it is running something called as CUDA blocks. Within each block, it was running 64 threads, and how many rows and number of threads were basically done. So this is the part of the first exercise. The second part is, if you want to take more control on the chunks values and how you want to, so in the previous case we left it up to the number and up to the apply rows to basically define at what chunk level the data gets divided. So tomorrow what we are going to do is we are going to first understand how the data gets divided among the CUDA blocks or CUDA threads, and then we will look at the apply chunks button, which is much more which will give you more performance as compared to blindly just calling apply rows. So with that, we are kind of done with the first part, and I will look at if there are